Unit 3 Chemistry, Chapter 8, Part 1, Chemical Equilibrium. So in this one, we'll be looking at what equilibrium is, why it is reached, and some graphs that represent the reaching of equilibrium. So, we've said so far throughout the whole of your science things that when we react two things together, they make the other things. Okay, so our products become our reactants. That's sort of true, but not 100% true. What really generally happens is that some of your reactants become your products, and some of them stay as the reactants. Okay, so the yield, yield is what percentage of your reactants become your products. In almost all cases, the yield is less than 100%. Okay, which means maybe 90% of them become your products, and another 10% stay as the reactants, and then you get a 90% yield. Okay, some of them are much less than that. So we'll start to see this double-headed arrow. Right? If we have a one-way arrow, we're saying everything on the left reacts to make everything on the right. If we've got a double-headed arrow, we mean, yeah, that reacts to make that. But also, these ones can react to make these. The reactions can go both ways. And that's why we don't get 100% yield. So the forward reaction happens, but also the backward reaction, and they happen at the same time. Okay? If we start off with just A and B, then they've got a really high concentration. Concentration of this is 0. So the rate of reaction of A plus B going forwards to make C plus D is quite high. As that reaction carries on, those concentrations fall, and as we know, if concentration falls, so does rate of reaction. These concentrations, on the other hand, increase, and as their concentrations increase, then so does the rate of reaction. And at some point there's going to be this magical point where the rate of the forward reaction and the rate of the backward reaction are the same. And that's the point that we call equilibrium. It's a dynamic equilibrium. Dynamic meaning still moving, because A and B are still reacting to make C plus D, but C and D are still reacting to make A and B at the same rate. So if you were to look at individual molecules, then they are still changing from one type into the other. Bonds are still being broken and remade. But if we measure the concentration, and then we measure it again 5 minutes later, they're going to be the same. We wouldn't have any net temperature change, because if one of them's endothermic, the other is exothermic, so the energy intake and the energy put out are going to be equal to each other. Okay? Reaching equilibrium, we'd see a graph that looks like this. Okay? So, this is our reaction rate. These are the reactants for our forward reaction here. Okay? They start with a really high reaction rate, and as the reaction proceeds, their rate of reaction falls because the concentration falls. HI starts with a reaction rate of 0 because we don't have any, but as we start making some, its reaction rate increases until we get to the point where those two reaction rates are equal to one another. Now they could be equal somewhere in the middle, it could be equal and down here, it could be equal and up there. We don't know, we just know that they're equal to one another. How far it proceeds, that depends on something called K. Okay? Any reaction, we can define the point at which equilibrium is reached for a given temperature. Okay? And we can work it out numerically. Okay? So this here is called an equilibrium expression. K is equal to the concentration of each of the products to the power of its coefficient. So if this was a 3, then it would be concentration of C cubed. If it was a 2, it would be concentration of C squared. If it was a 1, it would just be concentration of C. Times the concentration of any other products to the power of their coefficient. Over the concentration of each of the reactants to the power of their coefficients. Okay? So it's basically, to simplify it massively, products over reactants. So if the reaction has gone almost entirely to the product side, then products over reactants is going to be a very big number. So if we've got a big K value, we know the reaction has gone almost entirely to the right. If the reaction has barely happened at all, which might be the case in some weak acids that we'd see, then concentration of the product is going to be very small, concentration of the reactants is going to be very big, so therefore our K value is going to be tiny. We'll look at how we calculate K values in the next video.